that recording?
Do you turn on recording?
Yeah.
Do you turn on the mic on the recording?
I put it on screen recording, so I think it does.
You screen recording on that top.
Yeah. Is it time yet? Or... Wait, is it time yet? What time is it?
Not yet.
Yeah. Hey, do you wanna do your...
Where is it?
Huh?
Where is it?
Where's Welcome.
Alright, hello everyone. My name is Katie and I'm from Calberg. I sincerely hope that you've heard of us at some point during your Berkeley experience. But for those who do not know, we were founded 40 years ago by students. Ever since we have been funded and run by students. The basic premise of Calberg is that we hire professional staff to train students how to run effective campaigns on public interest issues so that we actually get stuff done. Public interest issues can range from everything from putting seatbelts in cars, which we did back in the 70s, with the help of Ralph Nader, to today when we just recently banned the plastic bag ban. Currently, we're working on trying to ban fracking in California, getting the UC system to go 100% renewable. It changes every year. We try to ask the students what their priorities are so we can respond accordingly. The issue today is that young people think that they are heard whenever they reach out to social media to make political statements. And until the day where people can engage in that way, even though it's extremely kind of impassionate and non-committal, until that day, you guys need effective representation, and that's what we're here for, so that you can spend your time preparing for your future so when you can change the world. These cards are how you become members of Calberg. The thing about Calberg is that we are funded entirely by students, and that we need 10% of students to pledge with us just in order to exist on campus. So what pledging looks like, it is $10 a semester. It obviously ends when you graduate, and you can de-pledge at any time just by emailing us. All we need is your name, your signature, and your student ID number, and also on these cards, you have the opportunity to sign our petition to either 1% renewable or ban fracking. Anyway, if you have any questions, fire them up quickly right now, and send these cards back efficiently and effectively so that you guys can get started with your class. Okay, thank you very much.
By the way, thank you all for voting.
Okay. Oh, do you want to collect the cards right now, or? How's everyone doing? Good. Middle of the week. Okay. Okay, let's get started then. Today we are going to be talking about some advanced topics. Last week we had an option on Piazza where you guys could send in some requests for this lecture. We had about 6 requests. Well, we tried to accommodate some of them. Requests we won't be covering, mining. We've kind of covered that in depth in previous lectures, so sorry. An in-depth look at proof of stake. We discussed proof of stake in the alternative consensus algorithms lecture. I think it's just tiny implementation details between platforms. If you're interested in understanding the nuances, just read up on different platforms. What drives the Bitcoin, Ethereum, and altcoin markets? That's sort of like asking what drives the stock market and what should I invest in. No one really knows. Supply and demand, I guess.
Speculation.
Speculation, yeah. How blockchain and Bitcoin is impacting the financial services sector. What impacts does blockchain and Bitcoin have on businesses, and how will it affect those industries moving forward? That's actually a really good prompt, and we have slides on that. If you're very interested in learning about it, come talk to us and we'll share it with you, but it's proprietary material, so we can't include it in the lecture. We're currently using that to pitch to companies, but do let us know if you're interested, and we'll send you that information. Same with crypto and finance, similar prompts. But requests we will be covering is blockchain for supply chain and some of the previous semester requests that we got. So let's get started. We will be discussing what some limitations of the blockchain are and some ideas to improve them. So one main limitation of the blockchain is that the information you store is expensive. Once you've stored information on the blockchain, it's sort of guaranteed to be on every node's hard drive forever. And that's quite a high price to pay. So we ideally want a decentralized file storage system. If we try to think of a proof of work solution of it, we would have issues figuring out how to update the Merkle tree or how to update the information in the consensus algorithms. But Filecoin basically proposes a solution on how to store all these files in a decentralized manner. You basically do this by maintaining a set of data pieces denoted by P, which keep growing, and Filecoin also implements proof of retrievability into their consensus algorithm. So how you would do this is anytime you mine a block of Filecoin, you find the proof of work to that block. That then becomes your partially mined block. You then take the partially mined block, which has a nonce, and use that nonce as some sort of a randomness generating function, and you hash this partially mined block to give you what is called an index, and then that sort of gives you a starting index, and you get a range of indices in which you will then store your file. And this range of indices are called your challenge pieces or challenge block. Once you find this challenge block, you have to then disseminate that information to the rest of the network, so it gives everyone else in the network the opportunity to store their block in these pieces. These pieces are continuously allocated. If they weren't continuously allocated, it would sort of incentivize people to have mining pools and just pool their storage spaces. Another cool incentivization Filecoin has is that the lowest mined blocks have the highest expectancy. So what that means is it's sort of incentivizing you to store the files which other people haven't stored. A longer-term solution is IPFS, which is basically called Interplanetary File System, which is sort of like a global file storage system. So every computer could then just connect to this global file system, and they don't even need local storage. Without going into too many implementation details of this, each file is basically identified by a unique hash. So if you want to locate a file, you just give the network its hash, and it gives you back the file. Some cool features which IPFS has is that it removes duplications across the network. It tracks version histories for every file, and only those files which you're interested in are then stored in the network nodes. The cool part about IPFS is that it uses a lot of non-blockchain distributed technology like peer-to-peer systems, or like distributed hash tables, which is what BitTorrent uses to keep track of information about its peers and its seeds. It also uses BitTorrent to create like multi-streaming. As you know, like torrenting something is faster than downloading it from a single source. IPFS also uses a Git kind of version control. If you used Git before, you might know that all of your commits are identified by unique hashes, and every future commit sort of like points to a past commit using like a hash pointer. It's built on this underlying Merkle directed acyclic graph data structure, which is very efficient and easy to implement. IPFS also uses self-certified file systems. I'm not too sure about what those are, but you should read up on it if you're interested. Some issues you have with any distributed system is the issue of decentralized identity. So like definitions for concepts like identity, trust, and reputation are very subjective. You can't define them in concrete terms. So also like applications of trust and reputation are highly contextual. So what that means is if you were to give everyone on the network a reputation, it would mean like you're assuming everyone has the same goals. So for example, what that could mean is if you're the mafia and you would trust everyone in the mafia, but that doesn't mean everyone else in the world trusts you. So one issue which a lot of applications on blockchain face, which want to build on reputation or identity or trust, have this issue of decentralized identity. OpenBazaar is a decentralized marketplace built on Bitcoin, which tries to solve this issue. Some features of it is that it has no fees and no restrictions on sales. OpenBazaar also consists of like 3 sorts of nodes. One, your vendors, your buyers, and your moderators. But it kind of gets sketchy when you have to depend on these moderators who are basically given a rating based on their peer-to-peer system. So it's no longer like you don't know how reputable the source is, unlike eBay or a centralized system. So how does OpenBazaar work? It sort of creates this global unique identifier for every vendor, merchant, buyer, moderator on the network, which is hidden. They can reveal it if they want to, but it's hidden to ensure preserved privacy. So the issue with it is, how do you prevent Sybil attacks in such an open marketplace? You would assume that your adversary, who is going to launch a Sybil attack, has infinite access to resources or funds or nodes. And so what stops them from creating multiple identities and giving themselves high ratings or high rankings? OpenBazaar kind of proposes a not so good solution, in my opinion, because it requires like a 30-second proof of work to create a new global unique identifier, which is not that much time, and someone could just every 30 seconds generate a new GUID. The next iteration that it sort of uses is to have a financial cost associated with giving a ranking. So you sort of like burn money to give someone a ranking or a reputation. And this is called a reputation pledge. So your reputation pledge can be implemented in 3 different ways. One is proof of burn, which is basically you destroy your Bitcoin to give rating points. The good part about that is you know for sure you're actually losing that money. But the bad part is you're just like unnecessarily destroying currency. The second is you can lock up your funds for a certain period of time. And then after that, you can receive your funds. But if you're an adversary who had infinite amounts of funds, you wouldn't mind locking up some funds because you know you're going to get it back after some amount of time. So that's really ineffective for Sybil attacks. The third is you could use security deposits. So sort of like if someone had to spend X amount of money, you need them to deposit something as collateral before they can spend that. You could sort of create an escrow account, and if any fraud is detected, you then like destroy their funds. It's a better solution than the above two, but it's like if you are creating an escrow account, you might as well have a centralized, efficient system instead of having an escrow fund in the first place. But assuming that the above three methods work or are good, we can sort of calculate the estimated cost of a civil attack for an adversary like Alex. So she was going to create multiple identities to give herself reputation points. To get to this current stage of reputation, she would have to spend $100. So one final approach is the web of trust model, which basically means we only accept ratings made by people you trust. But that sort of means every buyer has to voluntarily disclose their GUID, so they're no longer anonymous. So you sort of define a network of degree n, sort of like how many hops is someone away from you. So a degree 1 is someone's your friend or friends of friends. The three main variations of these are you either use proof of burn, which we discussed is not that great an option, or you can use something called line of credit, sort of like you trust certain lines of credited users, and if enough lines give you credit, then you can withdraw that money from your account. So Alice has 4 lines of credit in this image. The good part about this web of trust model is that you can run graph analysis algorithms to detect any suspicious activity, like the centralized node, which is just constantly giving others reputation, but not really receiving anything, could be deemed suspicious. But the fallback is that you can't really distinguish between what is a fake rating and what's an actual rating. So it's still not civil attack resistant. So the conclusion about this is either pseudonyms are anonymous or your decentralized reputation is pointless. To quote OpenBazaar, to put it plainly, no reputation system is resistant to a vendor purchasing their own items and making false positive ratings. So we'll now talk about security and governance. So Tezos is a smart contracting language. If you recall from all the Bitcoin block size debates, the community hasn't been able to come to consensus by themselves. Like the power lies with either the Bitcoin Core developers, like the Bitcoin Classic developers. So Tezos is sort of a smart contracting language which builds in governance into its language. So to quote Tezos, Tezos is the first and only blockchain implementation operating with decentralized governance. And in Tezos, governance is by consensus, not by roundtable. So what that means is the loudest person doesn't necessarily drive what is best for the community. Tezos markets itself as the only smart contract language which has formal verification possible, which basically means you can mathematically prove your code is correct. So if you recall back to the DAO hack where we lost like $1 billion of market cap, you could have ideally prevented such a situation if Ethereum had formal verification built in. So these are some buzzwords which Tezos uses on their website. Layered ledgers, operational, and dynamism. So we now sort of move into a governance system with like security and governance. Futarchy is basically a form of government. So to give you some sort of assumptions which you would have to agree with, you would basically assume that it is hard to tell the rich, happy nations. It is not hard to tell the rich, happy nations apart from the poor, unhappy ones. And democracies which fail because they are not aggregating information properly. And that poor democracies adopt these so-called dumb policies, and these dumb policies happen not because there aren't smart people in these poor democracies. It's just because that these smart people who exist are the experts. Opinions are sort of ignored. But you can't just take these experts and give them the power and have them run the government, because if you did, they would no longer act in the best interests of everyone, but they would sort of like act in their own interests, and then they would no longer be experts. So a proposed solution to such a governance issue is Futarchy, which is a form of government which is proposed by the economist and philosopher Robin Hanson. You basically are trying to use the democracy that you have to agree on certain economic goals or objectives. So we're trying to use prediction markets to determine which policies should be passed and which should be implemented. To put it in their own words, you want to vote values of your community and bet on the beliefs, like bet on the policies which you believe are going to make impact. If you recall, in like any election, prediction markets are often like the most accurate as compared to like media predictions or election polls. So you're basically tapping into this accuracy of prediction markets. So having a say in a policy sort of requires a financial commitment. So you're putting your money where your mouth is. So the experts are like people who think they know something, but they don't actually know it, will lose all their money in the markets. And those who know that they don't know anything and have just been giving out false opinions will shut up because like they're going to lose their money. It is unclear whether Futarchy can be implemented with blockchain, because that would mean all the policies have to be qualitative. But that's some food for thought. And now finally to the supply chain blockchain application. So one problem we're going to discuss is a conflict of diamonds, or a blood diamonds problem. So if you were to buy a diamond, you don't know if someone died in the process of making that diamond. Like this diamond could have been produced in some of the war conflict zones, and you don't know what is the cost of your diamond in terms of lives. So the Kimberley process is a notifiable effort. It's sort of like a multinational effort which requires government officials to certify that no one died in the production of this diamond. But the issue with that is you're sort of trusting that government officials won't be corrupt and they won't accept bribes and that they actually know the source of where the diamonds are coming from. The issue with supply chains is they sort of mask the actual path of where your goods go. So Everledger uses a blockchain to sort of keep track of these diamonds and prove that their origin, like no one died in the production of these diamonds. So as you all know, blockchain is a global immutable ledger, which sort of makes it a good idea to keep track of all the information tracking where this diamond has been. So you every diamond is sort of tokenized on the blockchain. And as this diamond moves along the blockchain, each person only accepts the diamond if they're also transferred in the asset on the blockchain, the matching asset on the blockchain. Because, so if I just accept a diamond without asking for the asset, I won't be able to prove to someone later on that this diamond was truly this is not a blood diamond. Why do we use a blockchain? Because it's immutable, duplicated, and cryptographically secure. So that means no one can go back and tamper with the records somewhere in the middle. Another reason is because it's open and transparent, so everyone would be able to see and keep track of the path. Even at the final destination, you have to check that the diamond actually matches the asset on the blockchain. Everledger is a decent use case for a supply chain blockchain, but it's not the general case. Some major drawbacks with the supply chain is that how can you prove a physical good matches a blockchain token? Sometimes counterfeit goods could be swapped in place of real goods. So if I was producing electronics and your phone had an ID, I could just print the same ID onto my phone and then send that around. So some possible solutions are create tamper-evident and hard-to-forge identifiers. So the example of just printing a unique ID on a phone wouldn't work because someone could easily duplicate that. But think of it if you grafted a dollar bill onto your product and had it such that if someone tried to take the dollar bill out, it's really evident that they've tampered with it, then that's a great unique identifier. How Everledger does it is they use the optical fingerprint of each diamond. They have advanced technology, so they can do that. But for any normal supply chain product, you're going to have to think of how you can create these tamper-proof identifiers. Yeah.
Sorry, what was the difference between the diamond and the asset?
So your asset is just sort of like the identifier of your diamond on the blockchain. And every time you move the diamond across, you also have to move the asset, transfer ownership of the asset across. Does that make sense?
Is there a way to do it so it does not transfer automatically?
The thing is how would you transfer it automatically? If I gave you the diamond, how would you ensure that you transfer it automatically?
Also, this process.
This
Ledger ensures that.
this sort of ensures that you shouldn't accept the diamond unless I also transfer the asset over to you. That's basically what it's saying. Yeah, because if you just accepted the diamond without the asset, you won't be able to prove to someone later down when you give them the diamond that this was not a blood diamond. Then you become sort of the originator. Another drawback is that you're sort of trusting the originator of the diamond to provide you the right information. Sort of like you're trusting that there was no blood diamond. The first person who gave you the diamond was honest. Yeah. Any other questions? Okay. So I think Philip is now going to talk about privacy.
All right, so I'm going to talk about some really interesting, more advanced topics in the privacy space. So the first thing I want to talk about is a really cool paper that Greg Maxwell wrote maybe 2 years ago called Confidential Transactions. What's really interesting about this is that he actually adds essentially a cryptographic primitive to the Bitcoin transactions that let you hide the values of each input and output in the transaction. So when you look at the blockchain as like a regular node or verifier, you just see a bunch of like cryptographic garbage. You can't actually tell what the values are. What's really interesting is he actually does this with some pretty simple like cryptography, like something that we can understand. And what's really wild is that actually even a verifier can validate that this like cryptographic garbage is a valid transaction. Like the inputs and the outputs both sum to 0, or the outputs minus the inputs equals 0, and so on. So how this works is first we've got to recall something from lecture 3, which was the simple hash commitment scheme. Basically, we had like Alice and Bob trying to like flip a coin. The key part here is that we have the commitment function, which takes some value x that we want to commit to but keep secret. And then we have a random nonce r that we use as part of the cryptographic, as part of the commitment protocol. So for example, we generate a commitment, little c, by basically taking the hash of the random nonce r concatenated with the secret value x. And then we basically give c, the commitment, to the counterparty, and they have this like cryptographic garbage. It's like, what do I do with this? Anyways, we use that in the protocol, and then sometime later we can actually reveal that this was a valid commitment by revealing our x and r values. And the counterparty can verify with the commitment function that this commitment was well formed. It turns out though that we can't use that simple of a commitment scheme where we just have like a hash of the random nonce and the value. We have to use something a little bit more powerful. There's a really simple and powerful scheme called Pedersen commitments that actually are homomorphic under addition. So what this means is that when you take two commitments and you add them together, it's the exact same as taking the commitment of the added values. So for example, if you have x1 and x2, which are your secret values, and you make two separate commitments to x1 and x2, and you add those two commitments together, it's the exact same as taking the commitment of x1 plus x2. And now the key part is that if like the secret values in the commitments are the same and you subtract them, it'll actually give you 0. And hopefully this should kind of make it clear why you can use this to like validate why transactions would be well formed. Because if the inputs or the outputs minus the inputs, or the commitments of the outputs minus the commitments of the inputs are 0, then it's a valid transaction. If that makes sense. So how do these actually work? We can use some basic elliptic curve cryptography, which we've kind of abstracted to just be like multiplication. So for example, we have some like elliptic curve generator points, G and H. You don't really have to know too much about elliptic curves, just that like you can do scalar multiplication like x times G or R times H. And basically our commitment function, where we're committing to x and a random nonce R, is basically x scalar multiplied with the generator point g plus r scalar multiplied by the generator point h. And so now what happens if we do the commitment of x1 plus the commitment of x2, we just like expand this out. We get like, the first commitment and the second commitment, and we basically just regroup the x terms and the r terms. And basically you get this like x1 plus x2 scalar multiplied by g plus r1 plus r2 scalar multiplied by h. And so this is basically the commitment of x1 plus x2. So crypto magic, it's amazing. Now, how we can use this in something like Bitcoin to give us confidential values is when we're creating a transaction, we basically just like, instead of putting, this output is worth like 5 Bitcoin, this input is worth like 7 Bitcoin, we basically commit or put the commitment to those values in the input and output spaces, but don't put the actual values. And the key with these Pedersen commitments is that like a validating node sees these commitments, they don't know what the actual values are, but they can like subtract the output value from the input value, and because of the way that Pedersen commitments are homomorphic under addition, it'll just give you 0. And they can see, oh, this is a valid transaction. So there's one kind of like key issue with this like really simple scheme, and I'm wondering if you guys can spot it. I'll give you a quick hint. So what if we make like one of the outputs a negative number? Maybe take like 30 seconds and just like think about what would happen or how you could exploit this. All right, does anyone have any clue or guesses? It's not super clear, but basically the key is if we like sub in some numbers, let's say we have a typical input, like maybe one input is 5 Bitcoin, one input is 10 Bitcoin, and then we put like negative 1,700 Bitcoin for one of the outputs. That means we can put one of the outputs to be 1,715 Bitcoin, and because the validating nodes don't know the actual numbers, they can't tell if it's positive or negative. And obviously a negative output doesn't really make sense. But we basically just printed like 1,700 Bitcoin for ourselves. So in his paper, he basically adds a key construction, which is called a range proof. We're not going to go into how these work, but basically it's a ring signature over like the bits in the values that let you prove that the values in the transaction are positive, essentially. There's a really cool paper that he wrote called Borromean ring signatures, so if you're interested in this, you should check it out. Now, some of the advantages of this confidential values is, it hides all the values in the transactions, so we basically get much greater anonymity and fungibility in our cryptocurrency. And what's really cool is that in the previous anonymity lecture, we talked about coin swap and coin join and all those things. And there were some issues where since you can see the values going in and out, you can maybe try to determine oh, this went here because of this fee amount and whatnot. However, if the values are blinded, it actually makes coin swap and coin join much more effective because we don't leak that extra information through the values side channel. And what's really cool is that this actually uses pretty vanilla crypto with really standard assumptions like random oracle model and discrete logarithm hardness of elliptic curves. So there's no crazy ZK snarks with trusted setup and whatnot. Of course, there are some issues with confidential values. It doesn't kind of hide values between participants, which kind of makes sense because you wouldn't want to take unknown amount of money. And it also requires interaction between the sender and receiver. They have to go through kind of ritual out of band in order to basically transfer over the random nonces. And there's also some small space penalty of a couple 24 bytes per input, I think. and that's basically for the range proof. Now what's really cool is basically last year, August of last year, there was a anonymous paper posted for the Bitcoin scalability conference called Mimblewimble, with the author as Tom Elvis Jedusor, which is the French Voldemort or something. So really weird stuff, but he proposed this really interesting protocol called Mimblewimble, which basically combines confidential value transactions, coin join, and this new concept called block merging to make a basically completely anonymous cryptocurrency that is super space efficient. And it's really interesting because, again, it uses pretty simple cryptography to the point where we can understand it. There are some things that it does, like removing Bitcoin script because it's too powerful. Just a note on that really quick. There have been some talks about re-implementing certain specific Bitcoin contracts under this system. So it's not totally giving you no power, but again, it basically uses super classic crypto that we can easily analyze. Now, how we're going to think about this is all the transactions in this Mimblewimble system are basically commitments. Everything is a commitment. There's no clear values, well, except for fees and block rewards. And again, there's no scripting. There's no pay to script hash. It's just basically super simple. The key is that we don't pay Bitcoins to an address. And we'll cover a little bit in the next slide, but basically we do this confidential values ritual where people are exchanging random nonces to build a new transaction, which is basically a set of output commitments. And then all you have to do is broadcast these commitments to the network, and because of the homomorphic addition property, they basically sum up to 0, and they can validate that it's a valid transaction. So basically all of the nodes on the network see these transactions that are just input commitments, output commitments, basically cryptographic garbage, don't know what the values are. The interesting part about Mimblewimble is that it doesn't have addresses, so the question is, how do we prove ownership of coins? Because in Bitcoin, when you receive money to an address, you can spend that output by proving that you own the address. In other words, basically making a signature from your private key that generated that address. In Mimblewimble, because we don't have addresses, so we don't have those private keys, we basically use the insides of the commitment as the private key. And there are some basic additional details that you have to add to make this work, but we're not going to go into that. Just kind of keep this simplified model. But what's really interesting is that you can get really huge space savings by using something called block merging. And kind of what we want to do is change our view of blocks as a list of transactions to instead being kind of just a single large transaction. Because the only thing that matters in this Mimblewimble system are input and output commitments. And once a commitment is spent, it's no longer useful. We can just discard it. So a block, we basically take all the transactions and smush them into a single transaction that just contains input and output commitments. In a kind of way, this is a non-interactive coin join across all the transactions in a block. What's more interesting is that we can actually take these blocks of these transaction blocks and basically add them together and take all the input and output commitments and smush them together into a new transaction block that is just more input and output commitments. And all the commitments that got spent in the previous block, we just remove because they're not useful anymore. And again, as a node that's validating blocks in the network, all you have to do is just go through sum all the output commitments, sum all the input commitments. If those two sums, or the outputs minus the inputs, is 0, then everything's fine. And we can just say it's valid. But we don't ever actually have to know any of the values. So using block merging, we can basically go from 100 gigabytes in the Bitcoin blockchain, where when you're syncing with the blockchain, you have to download every block and validate all the transactions, it's lots of hashing and stuff. Whereas with the Mimblewimble, system. You basically just like download the UTXO set, and that's it. Really cool paper if you guys want to read about it. It's really interesting. Up next, I'm going to talk about some interesting scalability features. For Lightning Network, there's something you can do called probabilistic payments for microtransactions. And if you don't know about microtransactions, it's basically like sending, thousands or millionths of a cent. And you would maybe want to do this if you're like, let's say you're watching a YouTube video on this like new blockchain platform where every second of video you pay for like, a thousandth of a cent. And that's like your watching charge. And instead of having to like, maybe pay for a single entire video and you maybe don't like watch the entire video, you can just pay for those like seconds each. Of course, making transactions on like, full transactions of the blockchain, you're gonna be paying like 50-cent fees. That doesn't make sense to like send, a thousandth of a cent with a 50-cent fee. So this is over like a payment channel where there's no fees because you can just like update your state contract. Of course, Bitcoin doesn't actually support like low value micropayments because at the current exchange rate, we basically got like $1 is 83,000 satoshis, and so if you want to send a micropayment of like 10 to the negative $6, which is like less than a single satoshi, which is the minimal value that you can send in Bitcoin, you can't send it because it's too small. And this will get even worse as the Bitcoin price rises because, if there's like $1 million per Bitcoin, it's like all of a sudden a single Satoshi might be worth like a couple cents or something. So this is like actually would be practically an issue if the price of a currency rises high enough. Now the question is, like, what if you want to pay someone half a Satoshi? We can kind of repose this problem as like, what if I pay you half a Satoshi or a single Satoshi with probability 1/2? And then like over a large number of payments, this kind of like averages out to half a Satoshi each. And the way this kind of works is like, if you've heard of the two-party envy-free cake cutting problem, which is like a really simple like thought experiment. We want to consider like we have two parties and they want to split a cake evenly, but they don't trust each other. So how this works is basically one person cuts the cake in two and the other person chooses which half of the cake they want. So obviously for the chooser, the best strategy is to like choose the largest half of the cake. For the cutter, because they know that the chooser is going to choose the largest half, their optimal strategy is to then cut it evenly in two. It's kind of like if you're taking 188, it's like the minimax problem. So the way this works at like a really high level overview, basically you have the divider and the chooser. The divider chooses the length of a hash pre-image and sends this hash to the chooser. The chooser then guesses the pre-image length based on the hash. And if the chooser gets it wrong, they actually get the Satoshi. Otherwise, the divider gets the Satoshi back. So that's kind of really high level. I'm kind of going to leave it at that because there's some like weird scripting implementation details. But there's a really interesting video by Taj Drija on these probabilistic payments, so I suggest you like watch that. Looks like we're almost out of time, so I think I'll skip this. Anyway, key assignment is the final paper. There's a prompt that'll be sent out, I think by email later tonight and also on the website. And there's no reading, so you know everything. All right, guys, have fun.
Wait, guys, quick announcement. If you like, so we have your final essay that we will release this week. Would you prefer that we have it due next Friday or during next week?
Okay. Also, if anyone has those like slips from Caliper, can you like give it to me? I also personally don't endorse Caliper.
Okay.